Good day and welcome to DCD New York, the industry's largest ever virtual conference. With New York City and much of the rest of the world in lockdown, we had to reschedule our live New York City event to the 1st and 2nd of September. But we didn't want to waste all the effort that's gone into producing a world-class conference program. So here it is, free to view for the whole world. I'm Stephen Warren, CEO of Datacenter Dynamics North America, and I'll be your virtual hall moderator for this session. As you've noticed, we're using the On24 webinar platform, which many of you have used before. But let me give you a little bit of some information. It allows interaction, unless, of course, you just want to listen. On the dashboard, you'll find the bio of today's speaker, some relevant papers that you can get to. But most importantly, there's a Q&A widget at the bottom, which you can use to ask questions. Hit Q&A. We'll try and fit them in as we go along. Scott will know what's going on. I'll be taking a look at them too. Remember, all the sessions are being recorded and can be viewed online at www.datacenterdynamics.com. So please send this out to your colleagues, send it out to your folks that you're working with, and let them know too. So, on to our Submer Immersion Cooling sponsored session, an exploration into the next generation of immersion-cooled data centers. With high-performance computing and artificial intelligence advancements driving rack densities to 50 kilowatts and beyond, the design and operation of the traditional air-cooled data center has rapidly begun to run out of breath. Join us as we discuss the opportunities and the challenges of machine-optimized immersion environment. And let's explore how a new type of cerebral fluid, I love that, enables significant evolutionary leaps in computing and energy. And one thing that Scott's going to do is he's going to really dig into the ramifications of changing in the traditional data center space, what we're facing and what questions whether need to be answered, and also whether robotics and autonomous operations could be the key in enabling a new machine-to-human synergy. So today our presenter is Scott Noteboom, Submer Immersion Cooling. Look, folks, everyone knows Scott. I've known him for decades. Okay, former VP of Yahoo, head of infrastructure strategy, design, and development at Apple. Scott Noteboom is also the founder of Litbit. We know the guy. Look, in his newly appointed CTO of Submer, he has the extensive experience in different fields, whether you're going back to his old days in video game development to web-based software and SaaS, whether we're talking about ISP to VoIP APIs, from cloud-based to open source platforms, from energy efficiency to renewable energy. Scott knows where we're going and what we're doing. And he's also got the insight into artificial intelligence and open source IoT platforms. And now he's ready for a new adventure in planning the future of highly efficient and brilliant data centers. So it's time for me to move backwards and move towards your questions. So please remember, get those Q&A questions up for our session. But right now, I'm going to turn it over to Scott. Please, sir, let's get educated.
Stephen, thank you very much. And welcome, I suppose. I'm sitting in my workshop in downtown San Jose, and I'm looking at like a 1941 Ford in a 29 Model A. So it's definitely different than New York City. And it's interesting when I look at this first slide and I see DCD New York, a lot of memories come into play. Mainly what normally would be happening is I probably would be complaining to my wife that I don't want to travel, getting on a long flight to New York City. I would be thinking to myself, why am I putting on this costume of this blazer and button-up shirt? And I'd probably be complaining to myself about that. And then I probably would be getting a little bit of social anxiety of being around so many people and needing to talk about so many things, because generally I'm a socially awkward person. And now here we are, and I'm sitting all by myself in my garage, and I'm thinking that New York City is one of the best cities in the world. And I remember the last time I did a DCD Prezo in New York City, I went to a Broadway show, The Iceman Cometh, and got to see Denzel Washington leave the side theater in disguise, walking down the street. That was fun. And you know, putting on that blazer today, now I think, boy, my mom would be proud of that. And you know, all the hugs and hellos and handshakes kind of sounds good after being locked in the house. So needless to say, it's good to talk to people, even though it feels like I'm talking to myself. and thanks for having me. So let's go into the first slide. So immersion cooling, really my goal of this presentation, first of all, is I joined Submer for really many more reasons, or quite frankly, a bigger reason than immersion cooling. But in an interesting thing, because immersion cooling and the fluid in particular changes the world, it's a big enabler of where I see things are going. So that's really what drives me here. So to get to the immediate issue here, you know, for the past 50 years plus, we've been building these air-cooled data centers, and rack densities were slowly going up. Now they're going up more and more. And some of us may believe the efficient number is, you know, 15 kW, 25. I hear people bragging even about 50. But as this compute density goes higher and higher and higher, which is really a dance between power and space density, we're running into the challenge of, you know, our data centers really running out of breath when it comes to air cooling. And when we have 70% plus of respondents indicating that rack power densities continue to go up, which I'm a big believer in, how do we address the question of, you know, what really happens when if data centers are running out of breath? And today we're going to talk about the premise of the 100 kW or even the megawatt rack problem. And what I tend to hit on here today is how we solve this problem of the 100 kW or even the imaginary 1 megawatt rack. By solving that problem, are we going to be enabling a new solution that actually takes that 100 kW rack or megawatt rack and turns it back into a 2 or a 5 kW rack? And a lot of that's the idea and the belief that I have when it comes to fluid. And I have a good influence in history to hopefully validate my case. By the way, I see questions coming in, and what I would encourage is, and normally in a presentation, we do Q&A afterwards. It's no fun to harass the presenter. But in this scenario, I completely feel free to harass me. I see Jack asking me what, no motorcycles in the garage? And my reply is I see 4 of them right now, so I just didn't mention them, Jack. So feel free to harass me or even ask questions along the way. Yeah, I do think we're going to be, Hamid, I think we're going to be sharing this PowerPoint presentation. So needless to say, if you have a question on a particular slide or you want to harass me or whatever, I'm actually enjoying the social engagement right now. So why are we running out of hot air? Because our data centers are full of hot air. Or sorry, why we run out of breath? Because the data centers are full of hot air. That's my cliche of the day. And when I look at this slide, I would say is being a person who's always trying to think of new ideas and such, I always kind of have a technique of every statement should drive a question, and that question should hopefully drive an answer, and that answer should drive the next question. So when I look at things, I look at the statements, and the statements I made here is we breathe air, we reside in air, and we need air to breathe. So therefore, I have these follow-up questions of, well, are machines kind of the same? And the point I'm trying to make across is in a lot of my career, I've been influenced by other things. I would say very rarely do we as humans innovate. So when it came to outside air economization, I remember looking at aluminum smelting plants. When it came, the chicken coop came from, you know, looking at chicken farms, and the next generation modularity ended up looking at, you know, BMW's Factory of the Future movement, artificial intelligence. I was studying the human mind. So what's interesting here is when it comes to this premise, I find myself looking inside myself, and I question, do I breathe air? Do I reside in air? And do I need air to live? The third question is true, but in the other things is I don't breathe air, my lungs breathe air. I actually, my body, I live inside myself. And actually inside myself, aside from the lungs, there isn't air. That the the lungs are just kind of an exchanger of cooling and oxygen. But I actually live in fluids. So when I look at myself, I actually realize that when I made these statements, I breathe in air, I reside in air. The truth is that's my body, that's not me. And when I go inside my body, which is where life truly exists in myself, it's not about air, it's actually in fluid. And what are the reasons that there's fluid inside of us? And what does that mean for my own computer in my mind? So on the premise of things, when I look at things, that's how I tend to look at things. And honestly, when I kind of quiet myself and go inside and look for those answers, I think the answers are inside of us right now. And I think nature and God, or whatever you want to call it, figured a lot of things out ourselves that apply not only to our computer inside our brain, but that could be applied to the computer in the data center. So let's quickly look at the human HVAC system. What's really interesting here is not a lot of differences. We have it's called the hypothalamus, the section of the brain that acts as the controller that receives sensor data via the spine, and we have a bunch of sensor data. We have that system controls the skin, and the skin really acts as outside air economization vents. And then we have our sweat glands, which are really the condensers of the human body. We've got blood vessels inside of us, which I suppose are kind of like the heat ducts of the human HVAC system. And then right below, in the middle layer of our skin, we have water storage to be used for cooling. That's used when heat basically activates those sweat glands. And then basically what we have is we have evaporative cooling going on. And then when we have evaporative cooling, we have chemical compounds in our body that's making our cooling more efficient. In this particular case, it's salt. So in the body, we learn the lesson that, chemical composition matters when it comes to cooling, kind of like in a quantum computer, cryo cooling, the chemical composition of liquid nitrogen. So needless to say, yeah, Paul, this is a little bit of a biology course, because we're going to try to look at how does this secondary cooling system, which is the human HVAC system, affect the brain or our computer, just like a secondary cooling system of air cooling, direct-to-chip cooling, or immersion cooling affects our system. So let's go into the evolution. So the fluid that I'm generally trying to connect us with here today is cerebral fluid in our mind. And that's where we're putting a little effort into. So really what we're gonna learn is when it comes to intelligent compute capability in biology or in the human body, or quite frankly, in the bodies of most any being that has intelligence, there is fluid that exists. Saltwater fluid, dielectric cerebral fluid. And what we find is when we look at our own bodies about 500 million years ago, either through evaporation or crawling up onto land, our minds transitioned from basically living in an oceanic saltwater fluid to the development of nature creating this cerebral fluid. So what gets really interesting is the way that I look at things is in the era of computing, where we have this race of when is the single low-cost computer going to approach the capability of the single human mind. And what's really interesting to me when it comes to cooling and such is these computers that we're discussing that will meet or surpass certain aspects of the human mind. We're talking 500 watts, we're talking 1,000 watts. What are the things that enable this human mind to operate at 20 watts and under? And how is the mind able to have performance and last longer than a computer and have its compute density higher and be very reliable? If our minds fail, we die very quickly. There's no swapping a brain like there is a CPU, stick of memory, or a hard drive. So that's looking at the question of why our brains remain more efficient than computers. So first of all, what I'm proposing is that biology shows that a dielectric fluid environment is optimal for computing and communications in the mind. So that's the exact reason that instead of needing 500 or 1,000 watts for our comparable electronic computer, our human computer operates 50x more efficient. From a space density perspective, it's efficient. From a component reliability and energy efficient perspective, if we're as inefficient as the computer and our metabolism system was still the same, imagine having to consume 50x more calories just to keep your brain working. And then from environmental efficiency, obviously we're saving that food as this an example. So we have a whole bunch of kind of examples and lessons to learn from this fluid objective. And thus the exercise that I've been involved in from a technology perspective is, are we really creating a cerebral fluid environment for machines? And what does that mean in the industry, from trying to immediately solve the problem of perhaps the air-cooled data centers run out of breath, to carrying us through the middle ground of what does our data center look like? Because if 1% of things are fluid cooled today, I don't know the percentage between immersion cooling, direct to chip cooling and such, and 99% is air cooled racks. What happens to the data center as that 1% turns to 10% or 20% or 50% or even higher? How do we balance these ecosystems? And then more importantly, as we learn from the cerebral fluid environment, what if it isn't just high density load? What if the benefits of this cerebral environment that we see in our minds and our human computer is just as efficient in machines, that then thus enables us to use it for a lot more reasons than just being able to accommodate 100 kW racks as an example. So a couple examples, and this is work that's kind of going on right now, is so working with the compute manufacturers, you have to look at what does the compute and kind of space density look like in computers from a server perspective. And what's interesting is you have short-term concerns. The short-term concerns would be, the immediate ones. What does my warranty look like when I'm emerging this in dielectric fluid? But then you start to look at, once you validate that it's operating, which we have use cases in the company I work for around the world, what does computers start to look like in a fluid environment? Because obviously the brain wouldn't be the same if it was in an air environment. It would be impossible. So you start to look at things and go, the number one cause of failure, fans. There's no need for fans. The transference of heat sinks start to go away, or at minimum get really small, a lot smaller. When you look at our electronics, both of the equipment that you see, that the GPU has many fans in it, particularly as you get into more advanced GPU. The motherboard and the compute chassis itself is really designed as a big air plenum or an air handler for airflow to go across it. Otherwise, it doesn't work. So you start to look at things and go, well, what happens when we don't have to worry about that airflow and such? How do things get much denser, much smaller? And how does that fundamentally change the way computers look like? Can that server look twice as small or perhaps even more? When you look at the power supply, I mentioned fans, power supplies are another major part of failure. And when you look at the data of even today's capacitors and you realize, well, wow, if we can provide a more stable temperature environment for capacitors, even the old charts show that those capacitors, which by the way lend to a top 5 risk of failure in the data center, the power supply, last twice as long, and they're not even optimally designed yet. So the whole idea is your entire thing of space and compute density starts to get a heck of a lot smaller, smaller than this 1U chassis, 2U chassis card, potentially smaller than our own brains. And perhaps what if that computer chassis we're looking at right now looks as small as the iPhone that I have sitting right next to me? So there's a lot of exercises going on in regards to, it's not just about cooling, it's about how this fundamentally makes the brain or the computer look a lot different and be a lot more reliable, a lot more energy efficient, a lot more space efficient, so on and so forth. And again, if we're looking at this computer, which obviously this wouldn't be the one, but if that server is the one that reaches kind of a singularity moment in regards to being able to equal the compute performance of a computer, what about when that's 20 watts like our brain is instead of 1,000 watts, because this cerebral fluid is a major contributor of enabling those to happen. So that's fun. So that's compute. Now let's look at some power density, and this is kind of fun stuff. And it reminds me, and this even goes back to some of my Apple days and before, of starting to have some strategic meetings with the electric car space. So when you look at next generation kind of energy grid type solutions, and in particular, next generation battery solutions related to energy, most of the innovation is all happening in the electric car space. So we've been working with a notable electric car company here locally in the US, as well as there's a lot of electric car innovations happening in Asia. This module that we're looking at now, which is a lithium ion battery pack from a company called Xing, X-I-N-G Mobility out of Taiwan. These batteries are all immersion cooled. So everyone has been looking at the immersion cooled battery environment for electric cars. And the reason is why? And it's the same reason we have in computing, and in particular, the same reason we have in data center. What is the density of the power when it comes to the batteries? How much backup time does it give us? So I can tell you in our lab work, it's 60 kW in 1U, OU, because we're doing this in an open compute kind of lab work. So 60 kW with 5 minutes of battery backup time, that is what we're experimenting with. And by the way, the Xing Mobility, their modules present that density as well. So you have about 250 watt hours minimum per kilogram of density. And so when you put these modules together and you cool them with fluid, what you have is you have a lot more density. You have safety. So we're doing tests as well as all the electric car space where you're taking, they look like little nails and you're piercing cells inside this module, which then normally creates this cascading disaster of, seems like a nuclear disaster of fire and explosion when it comes to lithium ion. But the dielectric fluid can actually kind of absorb energy of multiple of those cell failures. So now you're addressing safety kind of concerns. Your recharge cycles and your discharge cycles. Again, in electric cars important, I would argue in the data center is important as well. The ability to discharge at a massive rate gives massive capacity, massive horsepower in a car, massive, I'd say, kW in a data center. Recharge cycles gives a quick recharge time in an electric car. You know, how can they recharge the batteries as quick as you can fill up your gas tank? And in a data center, recharge becomes important as well when you have recoverability of utility and such. And then in this space for electric cars, charge cycles are incredibly important. So they're working at 3,000 as a minimum and working upwards of how often can this battery be charged to 75% or greater and then discharged lower, because that's the day-to-day life of an electric car, which far surpasses what's happening in the data center. So what this really means, by the way, is when we talk about racks that are immersed in fluid, imagine the 1 megawatt UPS system in a half rack or a full rack type footprint that offers that level of backup time, that level of 1 megawatt capacity, that level of safety and fire suppression when it comes to batteries, that level of charge and discharge cycles at much higher levels at a longer life, we can really thank the electric car space for doing and making the innovations and the investments in this space. And I gather that a lot of these lessons are going to be carried forward into the data center space, which I'm most excited about, because when you look at the OCP movements, you can look at something and say, wow, in 2U of my rack, there could be a day where I have 60 kW of AC to DC conversion and 60 kW of 5-minute battery backup in 2U of a 60 kW rack. And that is something that is really compelling from the space. So how does this cerebral fluid affect us in the data center? So now how it affects designs in the data center. So if I'm a data center builder, the big things that I'm looking at is well, I still have 5 kW racks, and in the future, I'm still gonna have 5 kW racks, and now I'm gonna have 100 kW racks. Imagine what a wholesale data center looks like, a football field size kind of raised floor environment with 10 100 kW racks in it. That's kind of ridiculous. But then you still have the 5 kW challenge. You have this mixed environment challenge of you have air-cooled racks, which are the majority of the market. Now you have direct-to-cool that requires air and water cooling. And then you have immersion cooling that requires immersion and no air across all kinds of watts per square foot. So what I'm proposing here is we need to think about things. I would say modularity, skid-based systems and everything. We've definitely accomplished our goals when it came to modularity for speed of construction and scalability. I would argue that's, we've been successful as an industry keeping up with the growth of the cloud because of modularity that's enabled us to do this and be able to do things quicker. But I'd say we still haven't accomplished modularity when it comes to flexibility of service. So what are some of the things that we're looking like? Because it appears that things could require us to be more flexible. So flexible cooling. I've got air-cooled racks. I know how to do that. Well, no, now I have direct-to-chip cooling, and direct-to-chip cooling means that I've got a percentage of stuff that I need to give cold water to, which maybe that's the same water as my air-cooled air handlers, but maybe not, because that direct-to-chip cooling doesn't require the low temperature, let's say 55-degree chilled water temperature. Now I'm becoming inefficient by using the same water loop. And then my percentage of air versus water is varying by manufacturer. So now I'm a water and an air-cooled data center. And then when you get in immersion cooling, you've got air handlers that are useless because there isn't a need for anything. So as a data center builder, what do my flexible service options look like to be able to accommodate this transition? We're not going from air to fluid. We're going from air to largely mostly air to some fluid, then some more fluid. Then maybe we're touching our toes in the water in direct-to-chip fluid. Then we're going into full fluid. And then believe it or not, in the long run, that full fluid may end up decreasing the power density that we go back into the beginning of things. There's just more dense compute in it. So I think as an industry, we're gonna have to look at kind of dual water loops for increased efficiency. Where's my cold water? My 55, 60 degrees for air. And then I would argue the warm water loop, as I call it, will end up getting warmer and warmer and warmer as we continue to develop this fluid. And when I get into, let me see, I have a note here, is 60C. So in some of the immersion space, there's belief that, you know, there could be a water loop at 140F when server manufacturers are designing their gear for future kind of means. So again, that warm water loop can end up being a hot water loop. And then we get into a scenario where it's a closed loop system. There's no refrigerant-based cooling used at all. There's no evaporation of water. But the long story short is how do we facilitate this transition that we're already seeing today, yet the data centers aren't designed to deal with it and it's not going anywhere? So flexible power. I had showed you the UPS. Right now, if I'm deploying even on current OCP kind of solutions, where are my data center providers that have flexibility of, we'll provide the UPS, or if you don't want the UPS, you can provide the UPS. That UPS can be immersion cooled, that provides all the benefits that I show. Where's the proper temperature water to enable that to happen quickly in a combination of air and water? As we get into these better energy storage solutions, a big thing on flexible power that I'm believing in, or I'm a believer in, is you look at the drawing on the right, and it's basically a little bit of a simple architecture of Kubernetes, which is horizontal resource scheduling. And what's really interesting is the way this cloud software works is you can have nodes of thousands of servers, and these masters in the center box are looking at compute, memory, and storage usage on each one of those servers, and is balancing the load properly across all of those racks, looking at things from a CPU MIT perspective, a memory usage, and a storage usage perspective. And so basically it can increase the compute utilization of the server, which I would argue has gone from 13% in my early Yahoo days to the people who are doing it the best is 70% or greater, which arguably makes the server itself, just by using software, 5x more efficient. But then you get into something and say, well, wait a second, where's the inputs of power, cooling, and space into this? Where's the API that communicates with the Kubernetes Mesos, or the Kubernetes system, or Mesos, or VMware, or whatever, that is saying, hey, we have a power quality or a power capacity issue. I need you to move that load off of this node. We have a cooling issue in this particular quadrant. Don't send any more load here. Or space versus power and cooling ratio isn't working right. These Kubernetes masters can shift this load very dynamically, very automatically, and quickly. And not only that, but they're able to do that across geographies nowadays, because networking performance and the software performance is getting better. Now we have a scenario where data centers can shift themselves out of areas of data centers that are having problems on the facility side, outside data centers altogether if they're having problems. Now you get into scenarios where backup generators, perhaps you don't need them. The longest pole and the biggest environmental issue in building a data center today, perhaps you can start questioning those kind of scenarios. And so these are all kinds of different scenarios of, from a flexible power perspective, how are we accommodating the different types of computing, the different software that's controlling the computing, the Immersion Cerebral fluids that enable not only computing, but electrical systems to work that much more efficiently. That's really the future of the data center. When it comes to power, the biggest thing that we have to deal with is number one, this Immersion Cerebral fluid environment. We actually have the blood-brain barrier. We have the lungs that are basically connecting the dots. The lungs are basically a robot, if you think about it, that connect the functionality of the outside world, which is air, used to be water, now is air, to be able to accommodate to our real world that we live in. We don't live in an air environment. Pay attention to where you are. You're inside yourself, and we live in a fluid environment. So like the lungs, what is the robotic environment that enables these two things to work together? And it's interesting, I'm clicking the little robotic sample video in the right, and it's not working. I should have checked that with my data center dynamics folks. But needless to say that the image in the right is a short video of an early concept last year of a robot that's swapping an OCP node automatically. It's interesting in today's times with the virus and everything, how that could be potentially valuable. The premise is there are better means than hands to connect the cerebral fluid environment for electronic computing, just like there's better environments for hands between our own environments. So how we manage that fluid to air environment is so much more than human hands and human cable connectors and human grips on servers and such. Now we get into robotics that enables a lot of those things to function. And then when we get into robotics, the data center starts to look like the stacked warehouse that is changing servers, installing 10,000 servers, refreshing servers automatically, swapping them when they're failed, and dealing with the disconnect, with basically connecting the dots between the fluid and the air environment. So these are all some flexible space, flexible power, flexible cooling that is a big thing of what we need to look at in our data center. So in conclusion, I would propose that the running out of breath is what's finally outdating our grandfather's data center. I would argue that the data center that we have today, imagine how inefficiently or just how our minds wouldn't even operate if we took it out and put it in an air environment. There's a reason that nature gave our bodies a cerebral fluid environment for our spine, communications in our brain, our computing environment. And it all comes down to reliability, performance, energy efficiency, cooling, space efficiency, and everything that we talk about in a data center. And so all of these challenges are driving really new opportunities in the space. And like I said, what I really expect is today you see the 20 kW rack, we're seeing the 100 kW rack, in particular high performance compute environments today. Someday you're going to see the potential for the megawatt rack. Then you're going to see the emergence of this cerebral fluid environment that then is going to make everything efficient, so much so that eventually that same level of computing that would require the megawatt rack is now going to be back into the 10 kW rack. And thus we're going to be getting 10x more computing in the same amount of cooling. And then that same data center is going to enable that much more computing that then is better for the environment and the world, and it's more reliable and all this kind of stuff. So this is an intro of kind of the things that I'm working on, which is what does the smart DC environment look like in a world where a cerebral fluid equivalent for electronic computers that takes a lot of the lessons learned from the cerebral fluid of human computers. And that's what I have to share today. So thank you.
Well, Scott, thank you very much. That was a fantastic. And look, we're going to try and dip our toes in the water, that's for sure. So we don't have much time, only about 2 to 3 minutes. Some of the questions will be going to you by our wonderful conference producers. But one of the biggest questions, Scott, that comes back again and again, and this came in before with one of the Q&As, what are the objections? Everyone gets this. Everyone knows this works. Like you were saying, in the end, we're going there. I don't know if we're at the megawatt rack, but okay. But Scott, what are the objections to going toward immersion cooling? What's wrong?
So first of all, when it comes to questions, Stephen, one of the things I'd ask is, because I see that the reason I didn't address questions as I was going is I quickly knew I was going to run out of time. There's actually a number of people I couldn't. So I can follow up with these questions. So I think I can answer anyone's question after this if we don't get to it. But I disagree with you. I would say from a data center operator's perspective, change is a risky thing. And so I would say it's just almost as risky as, imagine if I was the crazy guy who was suggesting that we take the brain and put it into an air environment, and what's it going to take to do that? We would all be scared of that because that's putting our life at risk. To a certain degree, data center operators, change is potential risk is potential failure is potential loss of job and money. So the benefit that I see here is the data center industry is actually incredibly resistant to change. The good/bad news here is the physical act of running out of breath or getting out of breath, as I describe it, actually forces change to happen. And the good news is it's just like an outage. When change is forced on a data center operator, they get through the challenge. We get through the challenge. Just sometimes, whether it's an outage or a lightning strike or whatever, just sometimes we have to be pushed into the pool to be able to make those changes happen, because our job is to avoid challenges to a certain degree rather than address them. So it's really fundamentally a human challenge more than anything.
That's really great. Thank you. I mean, it's a perfect way to put it. Same question is, will there still be racks? Will there still be air cooling, do you think?
So this is my belief, and what I believe is in the midterm, absolutely. So I believe when you look at the fact that I'm proposing that we are going to re-engineer the mind of the computer, let's call that the server, that is a long-term path. And what I'll tell you in the long term, I thoroughly believe that in the long term, it doesn't remember, our brain only uses 20 watts. And I would argue that if our brain used 20 watts or 0.2 watts or 2,000 watts, there would be no discussion at all if being in a fluid environment would be optimal for that type of computing. And in the long term, that's the answer when it comes to electronic computing. Over time, which I'm horrible sometimes at predicting time, over time, everything is going to be in this cerebral spinal fluid environment for electronics. But over the fact that change is slow, there's no reason today, is there, to put a 5 kW or a 10 kW rack in fluid? There isn't a lot of reasons today. So I think that what we have to assume is that it isn't going to be option A to option B. It's going to be this, quite honestly, this painful transition between these two environments that actually makes the most interesting challenge that we'll figure out and work through.
Scott, thank you so much. And for everyone who is listening, that was just great. And by the way, I want to repeat something. Outside of this entire 3 days, you are one of the top sets of sessions that people are going into because they're so concerned about this issue. They're so interested in it. And again, I have to just say, Scott, to you and to everybody at Submer, thank you for all that you're doing, and we appreciate your time.
Yeah, I just want to say like one thing, and it's, you know, today is like so much not about Submer or me or really anything too much. So again, just to follow up, remember, we were all supposed to be in New York City, and New York City is getting hit harder than any place in our country with this virus. So, you know, my thoughts are is that everyone that I love that's in the city, and hopefully you guys are able to dial in as well. And to give a little positive note on that one, just to close personally, my presentation got thrown together pretty quick because my mom has been hospitalized with COVID-19, and that's a tough one. But to put optimism to my friends in New York City, she just got out of the hospital, and she was one who didn't really have an optimal health or environment or condition for this, and she got through it. She just got out of the hospital last night. So I think we as a New York City, we as a country, and in particular, when you think of we as a data center industry, we're all going to get through this. And if anything, this just makes our industry more exciting, more booming, and more helping for people going through this scenario. So I just wanted to give my kind of proper call out to that because it's interesting time. So thank you.
Thank you so much, Scott. Amazing words. We really do appreciate it. And to our entire community, what you've said is so perfect. Again, much appreciation. Folks, remember what Scott's just delivered will be available online. Pass it off to your friends. If you've got additional questions, get them up. And at this point, we're going to end our webcast. So thank you all for joining us. And up next, don't forget, Cloud Conundrums. Talk to you soon.